Discrete optimization. Welcome back. This is dynamic programming, okay? So this is the first lecture where we're really going to go into some technical details. So what we're going to do is basically show you how you can get the best possible solution to the knapsack problem. And we're going to use this first technique, which is dynamic programming. So in this class, what we are doing is giving you a lot of hats, okay, optimization hats. And these are different techniques that you can use for solving optimization problems. And we don't tell you really which one is good and which one is not good. Actually, we don't really know. But they will give you tools to actually look at these problems and try to solve them. And the first one that I'm going to talk about today is dynamic programming. And dynamic programming is a very widely used technique, okay? So when it works really well, okay? And for various classes of problems, it works very well. Particular example is computational biology. A lot of the sequencing problems can be solved using dynamic programming. But sometimes it doesn't work at all. And we'll try to give you the intuition why, okay? But this is a very useful technique when it works, as I said. Okay, so the basic principle is very simple. It's a divide and conquer approach. Okay, you know, you're going to split the problems in different parts. But the really important thing is that it's a bottom-up computation technique. Okay, so if you can do that in a top-down, divide and conquer in a top-down or bottom-up technique. Okay, and dynamic programming is about bottom-up. We'll see a top-down technique later on, also on the knapsack problem. Okay, so let's talk about dynamic programming. And once again, I'm going to assume the same conventions that we use when we talked about the modeling of the knapsack. So we have a set of items, capital I, and these items are going to be denoted from 1 to n. Okay, so these are the various items that I can pick up. They have a name which is 1 to n. And then I'm going to make another convention which is this OKJ. Okay, and OKJ is essentially the value of the optimal knapsack if the capacity of the knapsack is k, and you can select item from 1 to j. Okay, so this is kind of a sub-problem, and we're going to build from it. Okay, the way you can formalize it is exactly the way I formalize the knapsack, right? But this time only we look at the j, the first j item. Okay, so in a sense, you know, look at the problem here. You know, you see that I'm not using n there. I'm basically using j. Okay? And obviously what we are interested in is solving the problem where we use the full capacity of the knapsack, capital K, and where we use all the item. But we will be basically using this problem as a building block. So what I'm going to do is basically be completely outrageous. I'm going to assume that I can solve all the subproblems for a capacity k, any capacity k, and j minus 1 item. So I have this oracle, okay, Delphi oracle, that's going to tell me the optimal value for these two, for all these things, okay? I'm assuming that I'm basically given this, okay? So that's the oracle that I have, and that I can query. I can always ask, oh, what is the value for the j minus 1 item for this particular capacity? And I can query this oracle and get the value, okay? So the next, and what obviously I want to do now is add one tiny little item, okay, OKJ. So I know how to compute OKJ minus 1 for any value of k. And what I want to do now is compute OKJ for all the values of k as well. Okay? I'm just considering one item. And you're going to see it's pretty simple what you have to do. Okay? So the first thing you have to do is to find out if that particular item, if you have a capacity k, if that particular item can fit inside the knapsack, if its weight is lower than the capacity k. If this is the case, then there are two cases that you need to consider. The first one is whether you are actually selecting the item or not. Okay? So whether you are selecting the item. If you don't select the item, the value that you get is simply the value of the item with the same capacity and j minus 1 item. Okay? And we have the oracle to compute that. That's the value that you see there. Okay? So if the item fits and we decide not to select it, what you get is basically OKJ minus 1. Okay? Now you can select the item, okay, because we know that it fits. And in that particular case, what is the value that you get? Okay? You get obviously the value of the item because you put it inside the knapsack. And then you get the value, the optimal value that you can get by using the j minus 1 item and the capacity which is obtained by removing the weight from k. Okay? The weight of the item that you just selected. And as this expression that you see here is Vj plus the value of a, k, w, let me start out again. It's the value of Vj, which is the value of the item, and then O, you call this oracle recursively, with the value of the capacity K minus the weight of the item Wj, and then obviously J minus one item. And so these are the two things that you can do if the item fits in the knapsack. If the item doesn't fit in the knapsack, what do you have? Well, you are only left with the value of the J minus one item and the same capacity K. Okay? So we can build this beautiful recurrence relationship here, okay, which consider the capacity K and J item, and you basically re-express it as a maximum between these two values if the item can fit inside the knapsack, and otherwise it's simply the same it's basically the same value as you would get if you use only J minus one item. Okay? So you have this beautiful recurrence relationship, finding the best case when the item can fit, whether you select or you don't select the item, or if the item doesn't fit, you just, have the value that you could do with the J minus one item. Okay? And of course, you have to start from where, if the capacity is 0, there is no item that you can put in the knapsack. And what I'm basically claiming is that if you have these things, okay, you can compute the optimal value of the knapsack and which item you need to select. Okay? How do you do that? Well, let me show you. This is a very simple C program or Python program. You could write the same thing in Python to do actually that. Because you know what? Computer science is just computing this oracle for you for free. Okay? So you see basically OKJ. Okay? That's the function that we are defining here. Obviously, if J is equal to 0, there are no item. Okay? There is nothing you can do. Okay? Therefore, the value is 0. Otherwise, you look at the item J and whether it fits or not in the knapsack. Okay, so you have the capacity K, you have Wj. If it fits in the knapsack, what you have to do, the optimal value of the knapsack is going to be the max of this expression. Okay, and once again, this consider the two cases that I have discussed before. And otherwise, if it doesn't fit, you simply call the function recursively. That's the oracle, right? With one fewer item and the same capacity. Okay, that program is actually computing the optimal value for the knapsack. Okay? Now, one question that I have for you is that, is this actually efficient? Okay? Can you tell me how efficient this algorithm is? Okay? And let me use an analogy here. This is, what I'm going to show you is a program for computing Fibonacci numbers. And it's basically the same structure, a little bit simpler than what I've shown you for the knapsack problem. Okay? If we want to compute the value of the Fibonacci number of n, okay, if n is equal to 0 or 1, okay, the value is 1. And otherwise, is the value that you obtain by computing the Fibonacci of n minus 1, n minus 2, and adding that to the Fibonacci of n minus 1. Okay? That's how you can compute Fibonacci number. And I have the same question for you, right? Is this efficient or not? Okay? And what you can see here is that, okay, so if you want to compute, when you look at this one, the value of Fibonacci n minus 1, what will you have, what do you have to do to actually compute that value, right? So you're going to compute this function, and you're going to compute Fibonacci of n minus 2 and n minus 3. But you just have computed Fibonacci n minus 2, and for computing that, you have computed the Fibonacci of n minus 3 and n minus 4. So you're basically recomputing many, many, many times the same values, okay? So this program is actually very, very, very inefficient, okay? You never want to use anything like that, okay? And why? Because in this particular case, it's top-down and we are not doing anything fancy, okay? So what I'm going to do is take exactly the opposite approach, and we're going to do a bottom-up computation, okay? So we're going to start with 0 item, and that's what dynamic programming does, right? We start with 0 item, and then, as I've shown you before, we're going to put 1 more item, and then 2 more items, and so on, until we have selected all the items, okay? So in a sense, look at this program here. This is the program that I'm going to use in the next couple of slides. The first thing we're going to do is, we're going to look at what you can do with 0 item, then 1 item, and then 2 items, and then 3 items. That's what we are trying to do here, okay? We are going to solve these very simple subproblems. They are very simple, and then we're going to build on top of them by adding 1 more item at a time, okay? And you're going to see, it's beautiful. Okay, so this is, and so when you think about dynamic programming, you can, a lot of people think about tables, and I'm going to show you the table intuition of dynamic programming. Okay, so you start with 0 item. How much value can you get if you have 0 item? Okay, the value that you get is 0, right? So there is nothing to take. Okay, now we are looking at 1 item, and assume that this item has a value which is 5 and a capacity which is 4. Until you have a capacity which exceeds 3. which exceeds 3, then there is nothing that you can get. You get no value, right? And then, essentially, as soon as the capacity is 4, you can get the value of the item. So this is amazingly simple, right? So we have one item, okay? Now let's look at what happens if we have 2 items. We get a new item there. Its value is 6, and its weight is 5. Okay? And once again, until you get one item that can fit in the knapsack, you get nothing. So initially you get all these zeros. And then you get to the point where the capacity is 4. When the capacity is 4, you can get the first item. So you get a 5. Okay? When the capacity is 5, what do you get? Well, you can select the second item, which is more valuable. Okay? And that's what you get there until the point where the 2 items actually fit inside your knapsack and you get a value of 11. Okay? So that's the second column. Okay? So 2 items. Now we're going to build on this second column to actually build the case where there are 3 items. And this is where things are becoming more interesting. You can see that the weight of this guy is 2, its value is 3. Okay, so as long as we don't have at least 2 units of capacity, there is nothing you can do. Okay, when we have 2 units, we get basically this item, the third item, 3. And now this is where things really start getting interesting. Okay, so in this particular case, when you have a capacity of 4, there are 2 items that are fitting in the knapsack, right? So this guy fits in the knapsack, and you can decide to take it or not to take it. If you don't take it, what happens? Well, you get the value that you would have, that you have when you select only the first 2 items. Okay, so you know that you will at least get the value 5. Okay, because if you don't do anything, you don't select the item 3, you get the value 5. But now you have also the possibility of selecting this guy. If you select this guy, you get its value, which is 3 in this particular case. But then you also have a non-empty, capacity for the knapsack in this particular case. What do we get? We get 1, okay? 2, we get 2, but the value there for 2 is 0, okay? So basically you get the value 3 plus 0, which is 3, and therefore it's better not to select the item, and that's what you get at that point, okay? And this is the same for the next column, you get 6, okay? This is another case which is very interesting, okay? So you are looking at the capacity of the knapsack, which is 6, okay? And you can decide if you select the item or not. If you don't select the item, you get the value which is on the left, which is 6, okay? But if you decide to select the item, okay, so you get the value of the item, which is 3, and then what you have, you still have a capacity of the knapsack, which is now 4, and you can fit the first item, which basically means that in this particular case, you have a value of 8 for the particular knapsack, okay? So this is really, really interesting now. Essentially what you do is you have to look at 2 values. The value just on your left, and that's the value where you decide not to take the item, or the value which is at the previous column, but where you have removed the capacity of the items that the weight of the item that you get. You get another capacity for your knapsack, and now you know that you have solved that particular problem, and you can use the value, right? So this is what dynamic programming does. It recomputes this new column, okay, based only on the previous column and 2 values in that column. Isn't that beautiful? Very, very simple, okay? Now you can wonder, but where is the optimal value of the knapsack? And this is there. This is my precious, right? 11 is the optimal size of the knapsack. I know that this value here at the bottom right corner is what I want, okay? You're going to say, yeah, but that's the value of the optimal knapsack. What is the optimal solution? And I'm going to show you now how you can actually get that value of the optimal solution. The only thing you have to do is trace back for my precious until you get to the beginning of the table, right? So what you do is the following. You look at the value of where you are, and then you look at the previous column just on your left, okay? If the values are the same, what do you know? You know that you haven't selected the item, okay? Because the value with 1 fewer item is the same, okay? So you know that the decision variable for that particular item is 0. You haven't selected that item, okay? Now you look at this value and you do the same thing, okay? So is this the same as that? No, it's not. That basically means that you selected item 2. You remove the weight of that item, you get another capacity that you can use for the remaining items, okay? And you do the same here. 5, is the same as 0? No, that basically means that you selected that item. And so basically at this point, you know that you have selected item 1 and item 2. Okay? So that's the optimal solution. And once again, the only thing that you have to do is take the bottom right corner and trace back inside your table, and you have the optimal solution. Okay? That's the beauty of dynamic programming. You compute this table, and then you trace back, and you get the optimum value. Okay? Now, let me show you a more complex example. Okay? This is a more complex example. Okay? It has 4 variables and the numbers are a little bit bigger. We want to make your life a little bit more miserable. Okay? That's what we do in this class. And so what you see is you see the table now. It has 4 entries. It has a bunch of capacity as well. Okay? And now what you can do, okay, you just stop this video and then you start filling this beautiful table on your screen. Actually, don't do that, right? So don't do that. Okay? Just print the lecture. Okay? So I'm going to do the work for you. Okay? This is the complete, the complete values for all these tables, and they are entirely correct. Okay, you can trust us on that. And then you see this bottom right corner, right? That's my pressures. That's what the optimal value of the knapsack. And then that's what I can use to trace back the value of the optimal solution. Look at this guy. Okay, it has value 44. Is it equal to 42? No. So you know that you selected item 4. Okay, so you decrease the capacity by the weight of that particular item. You get to this position. You see, oh, is it the same? Oh, yes, it's the same. Oh, yes, it's the same. Oh, it's not the same. So you know that you selected item 1. So the optimal solution here is selecting item 1 and item 4. Okay? So, and the value of your decision variables are exactly that, right? So you see that x1 is equal to 1, the next 2 are equal to 0, and x4 is equal to 1. Okay? So this dynamic programming algorithm here is basically computing all the value of your decision variables and satisfying the capacity constraint. Okay? Now, an interesting question for you is, how long does this algorithm take? Well, it's pretty easy, right? So the only thing that we are really doing is filling this table, okay? And to fill any one of the entries in this table, the only thing that you do is looking at 2 values on the prior column, okay? So it's basically an algorithm which takes, the time that it takes is, asymptotically k times n, where capital K is the size on a knapsack, and n is the number of items. Okay? Now you're going to say, wow, this is really interesting. We just solved P is equal to LP. This algorithm is polynomial, right? Right? So are we going to get a Nobel Prize? No, not really, right? So why? Because on a computer, this capital K there, okay, can be encoded using binary notation by log of K, capital K bits, okay? And because of that, when you look at this complexity, it's actually exponential in the size of the input, because I can encode this input with log K bits, okay? So this is obviously exponential in that number, okay? So what do we have here? Well, we have an algorithm which is called pseudo-polynomial. That basically means that if these numbers are small, this algorithm is polynomial. It works very well when the numbers are small, okay? So every time, you have essentially a knapsack whose capacity is reasonably small, this is a very, very efficient algorithm. If the capacity starts getting huge and huge and huge, and you have a lot of items, you are going to get into some issues. And can you guess what the issues are? Okay? Remember, what we are computing is this table. Okay? If capital K is huge, this table is going to get bigger and bigger and bigger and bigger. Okay? And that's one of the problems that you have with dynamic programming. Okay, guys? So this is the first hat, okay, that I wanted to present to you. This is dynamic programming. Okay? So you saw how we can compute, optimal solution to the knapsack problem with dynamic programming. In the next lecture, we'll see another technique, which is essentially solving this recursive equation using a top-down approach. Okay? See you next time, guys. Thank you.